Today I'm going to talk about some of the lessons that we learned at Duo building a BeyondCorp inspired SSH proxy. Before I do that, I'll quickly go over the agenda here. So I'll start by just briefly covering what BeyondCorp is. Then I'll talk about one specific part of the BeyondCorp model, which is the access proxy. And then I'll move on to talking about how we were able to tunnel SSH traffic through the access proxy. And then I will cover the client and server implementations of that. And then hopefully we'll have time for questions. So BeyondCorp. You've got data and attackers want him or it. So core to the BeyondCorp philosophy is the idea that walls don't work, that a perimeter is not sufficient to keep attackers out. So BeyondCorp is a re-envisioning of the corporate network by Google. It was introduced by Google that shifts access control from the perimeter to individual users and devices. And the end result of that is that users will be able to access corporate resources that without a VPN. So in this case, it wouldn't matter if you're working from a coffee shop or a plane or your company's corporate headquarters, you would get the same checks. So it's like as an example, let's say that you have a company lunch menu, and in order to view the lunch menu, you just need to have a managed device, or but to access like source code or like anything more valuable than that, maybe you'd have to have not only a managed device but have the latest security patches and so on and so forth. So BeyondCorp is a pretty complex system, and it's been discussed at length, most notably in like the Google research papers that they make available. But today I'm just going to talk about one part of it, which is the access proxy, which is responsible for gating access to internal resources. You can think of it kind of like a reverse proxy. So the access proxy. This is obviously an oversimplified diagram, but hopefully you'll get the idea. You have external clients, or in some cases internal clients, that want to get to stuff. And the access proxy is responsible for determining if the user and the device are authorized to access that resource. And before I dive in too deeply, like on the implementation and like other things, I'm just going to get some terminology out of the way. So I'll use the term access proxy throughout this talk, which in this case refers to a web server and a reverse proxy that is responsible for authorizing and proxying requests, whether it's like HTTPS or SSH or RDP or whatever. And then a service, which is any application or server that sits behind the access proxy. So to dive in a little deeper on the access proxy, it's a web application that handles determining whether a user is authorized to access a service, and then a reverse proxy that communicates with that web application to basically ask, is this request authorized? And if so, it'll allow it. And again, going in a little deeper on the services, in practice is just a DNS name. So you could have like wiki.example.com or sshserver1.example.com. And each one of these services in the access proxy parlance will have an external name and an internal name or IP. And then again, users are authorized to access services by the access proxy. So the most obvious use case for this was web applications. So when we initially built this at Duo, that was the first thing we wanted to solve for, mostly because that's like every employee needed to access at least one web application that they would normally have to access through the VPN. And we wanted to give our employees a way to do that without having to use a VPN. So that's what we solved for. So I'm going to talk a little bit about the authentication flow of the access proxy. There's a really handy feature in Nginx, this auth request directive, which handles authorization based on the result of a sub request. So I mentioned earlier that the access proxy was a web app and a reverse proxy, and that the reverse proxy basically asks the web app, is this authorized? Is this user and device authorized to access this resource? So auth request is a perfect candidate for that, because it will return, so if a sub request returns a 200 response code, then the request is considered authorized and then is allowed. If it returns a 401 or a 403, access is denied, and then any other HTTP status code is considered an error, and the request would be denied. So, like you can imagine, in this case, there's a sub request that checks for a valid session cookie for that particular service, say wiki.example.com. And for unauthorized requests, we would initiate an SSO flow by returning a 401, and then having Nginx redirect to a login URL that we specify in a header. And then eventually Nginx proxies the authorized request to the backend services. So to give you an idea of what that might look like, at least with Nginx, we specify this auth request directive up here, and point it to this /verify handler, which is an internal handler, meaning that it's only accessible to the reverse proxy and not externally. And then we also set, if a 401 is returned, we set this header here, which is the access proxy check header, to whatever the upstream web server set it to. And that would cause the Nginx to redirect you to the SSO login if a 401 was returned. And don't worry about like writing any of this stuff down. Like all the slides will be available. So how would you, now we'll get to talking about SSH. Like how would we do this? Tunnel SSH traffic through an access proxy. It's not as obvious as how it would work for web applications. And the reason we really wanted to do this is because SSH, at least at Duo, or in my department at least, is like the second most common thing that we need the VPN for. So that was an obvious next choice in like the type of the next obvious protocol to choose. And so when we set out to build this, we had a few tenets that we wanted to stick to. The first one, Google actually calls this out in one of the BeyondCorp research papers, is that it should be really, really easy to add new services behind the access proxy. Like if it takes a day and a half for you just to like put the access proxy in front of your lunch menu, then no one's going to use it. So that was important. Another thing was that we wanted to have this work with existing SSH tooling, so OpenSSH, as well as the Chrome Secure Shell, because we're big fans of Chrome OS. We didn't want to, for example, write our own SSH client to be able to tunnel that data through the access proxy. So we wanted it to work with everything. And then we also wanted to use a browser-based authentication flow. And the reason was that if we used a browser-based authentication flow, then we could keep the same authentication method that we used for web applications. Another thing we considered important was that this access proxy should be transparent to the backend, regardless of the protocol. And for non-HTTP protocols, WebSockets ended up being a good candidate for this. So turns out Google actually talks about this as well in the BeyondCorp research papers in part 3, the access proxy. And they specifically call out this proxy command facility, which I'll talk about later. They also describe it as easy, which I generally disagree with, but maybe it is for Google. I mentioned Chrome Secure Shell. We're big fans of Chrome OS at Duo, so Google makes this Secure Shell Chrome extension available, and it's open source. And it has support for the so-called HTTP to SSH relay. In the comments for this, in this specific file, Google mentions that there are no public relays available, nor is the source code for their relays available, but there should be enough information for you to build one of your own. So that's what we decided to do. And yeah, that made us pretty happy. So this is actually what the Chrome Secure Shell looks like. So I'm going to show you this workflow for Chrome Secure Shell and then for standard like OpenSSH command line on macOS. But in the Chrome Secure Shell case, there's this text field, which you can't really see here, but I have it in a later slide. But below the username and the host, there's these relay options. And you can specify the relay server to connect to, as well as the port to use and whether or not you want to use SSL. So I'll show you what that looks like. So this is already in the browser. So we just redirect to like the access proxy URL and handle, determine if the user and the device are authorized. And then once we determine the request to be authorized, we redirect to this Chrome-extension : URI scheme that actually like points it to the Chrome extension ID itself with a few other parameters. And then I'm able to tunnel those bytes through the access proxy. So all of those NAND-GET bytes are tunneling through the access proxy. So what does it look like on macOS or like Linux or Windows or whatever using standard SSH tooling? So I mentioned proxy command. This takes advantage of that facility. The user types, username, whatever, SSH host. We launch the default browser, handle the device authentication, and then once we determine the request to be authorized, we redirect to a local host in this case, or like to send the credential, like the cookie that we need for passing that data through the access proxy back to the to the client. So, and then again, just log in as usual, and it's NyanCat all the way down. Okay, so how this works in a nutshell. For Chrome Secure Shell, we have the Chrome Secure Shell client, which communicates with the access proxy that you specify over WebSockets, and then eventually those bytes just make their way to the backend service. For OpenSSH, it's a little more complex. So we have a client, that being the SSH client in this case, launches our external program, which is just like an on-demand proxy using this proxy command facility. And then our client is a WebSockets client, so it sends the SSH bytes through the access proxy, and then eventually, the access proxy will unpack those WebSocket frames and send it to the back end. So this is a simple like data flow diagram showing like what this looks like for Chrome Secure Shell. You have a series of HTTP handlers as well as a WebSocket handler. And that's all defined in that NASSH Google Relay.js. Yeah, so I'll have more time for questions at the end, but yeah, basically this, yeah, you're right, that this is only doing authentication at the time when the user logs in, not continuously. Now there could be like additional work to be done to like limit the amount of time a session can exist and so on and so forth. Or like if you wanted to like visibility into the SSH traffic that was passing through the access proxy. Like you see those bytes. So, but you're right that like this particular example isn't doing any type of like continuous authentication. I mean, in our testing, it hasn't. It's actually been pretty okay. So, I mean, but that definitely is a concern, and the solution to that would be maybe more access proxies. So if you were concerned about load, but I'll move on for now, and we can talk later about that. But again, so and this is the next. So this is the diagram showing what it looks like on for Mac OS, or not Mac OS specifically, but using OpenSSH with the proxy command facility. So next I'm going to talk about the NESSH relay protocol, which is what is described in that Chrome secure shell JavaScript file. And so again, getting terminology out of the way, NASSH is synonymous with the Chrome secure shell. So anytime I say that, you can just think Chrome secure shell. But that is described as a Chrome app that combines HTerm with a NACL build of OpenSSH, blah, blah, blah. So what is native client is that is a sandbox for running compiled C and C++ code in the browser. And then HTerm, which is an HTML terminal emulator. So just in case you were wondering. So like I mentioned previously, Chrome Secure Shell supports this NASSH relay protocol. It's documented in that file right there in that path. NASSH.js, NASSH Google relay.js. Again, Google doesn't provide source for the relay itself, but they describe it as an HTTP to SSH relay that uses WebSockets, and the handlers are all documented in that file. And the cool thing about this is, like I said, we're big fans of Chrome OS at Duo. So by following this protocol to the letter, this just worked out of the box with Chrome Secure Shell, which was great. So this NASSH relay protocol is an HTTP to SSH relay protocol that's supported in Chrome Secure Shell. Like I said previously, defines a series of HTTP handlers, which I'll talk about in a little bit, what those are exactly. And then at its core, the bytes that pass through the access proxy are just the SSH payload itself, plus this custom like ACK, which again I'll talk about. And then it's, I guess, worth noting that it uses WebSocket binary frames as opposed to UTF-8 frames. So WebSockets. Just wanted to quickly talk about what WebSockets is. So it's message framing layered over TCP, and it was designed for two-way communication between browsers and servers, so that you wouldn't have to open up multiple HTTP connections. But of course, you're not limited to using it in browser contexts. We use it in our local on-demand proxy. And this is also something that Google talks about in one of the papers, is that it allows you to separate the device authentication from user authentication. That's why, for example, I launched the browser, I'm determining whether the request is authorized, and the user, but not actually, we're not authorizing that SSH login. That's still handled with your SSH key or password or whatever. So WebSockets it starts out as an HTTP request, an upgrade request. And once the connection has been established, the server responds with an HTTP 101 switching protocols, and it gets upgraded to a persistent connection. And then also both the client and server are able to close the connection using this close control frame, which is not honored by Chrome Secure Shell, which I'll talk about later. But there are other ways to close the connection. So just real quickly, this is what a WebSocket upgrade request looks like from a client. So this is the client handshake. And then this is the server responding with, yes, we're going to switch protocols to WebSocket. And then this is a WebSocket frame. I'm not going to talk about all of it, but just so you can see it here, the opcode is defined. It's just those 4 bytes there. And the rest of it's just, protocol-specific stuff. But we'll talk a little bit about the different opcodes that we're using in this example. All right, so then within the WebSocket frame, we have our own frame which is just an ACK plus the SSH payload. So this is what the client would send, would prepend to the SSH payload when it passes it through the access proxy. And this ACKing protocol or whatever is used so that the client and server can keep track of the bytes read and written. So when a new connection is established, the client will send the ACK offset in the query string. So when it's a brand new connection, that would just be 0. But on reconnects, it could be non-zero. The server then sends the contents of this retransmission buffer minus the ACK offset. So the retransmission buffer, what is that? It's just a buffer of the bytes that the server received, or that the access proxy received from the back end. And then we just trim that every time we receive an updated ACK from the client. So I'm going to talk a little bit about the server implementation. Yeah, so this is what an Nginx config file might look like if you were to add WebSocket support. There's just 3 lines that you need to add to an Nginx config file to allow WebSocket connections. We also use this framework called Cyclone, which is a Python web framework, which has built-in basic WebSocket support. There was a minor modification required to get binary messages working with, or binary frames, but wasn't too bad. It's worth noting that I think most web application frameworks these days have at least limited support for WebSockets, so it wouldn't be even if they don't, there are libraries available. So now I'm going to talk about these 5 HTTP handlers that are defined in the NASSH relay protocol. There's cookie, proxy, read, write, and connect. But we really only need to implement 3 of them because read and write are the HTTP handlers that you would use if you couldn't, for example, support WebSockets. So the first one, which is /cookie, this is responsible for handling authentication and authorization. And then we'll do the 302 redirect to either that Chrome extension URI scheme or to localhost. And then /proxy, this is responsible for opening the TCP connection. So when the client hits /proxy, it specifies the server and port that it wants to connect to, and then the server is responsible for opening that connection to the back end. And then it returns a UUID that is used for identifying the connection going forward. And then the /connect is the actual WebSockets handler, and that is responsible for just the bidirectional communication between the client and server. So I think I said earlier that I would have a better screenshot. It's still kind of hard to see, but this is those relay host options below there. So that's one client. The other client, just regular SSH. We did, like I said, we had to create our own on-demand proxy. We wrote it in Golang, which it uses the proxy command facility, we don't use it directly. It is launched by proxy command. So proxy command, if you configure, for example, in your SSH config file, that for a specific host, say star or whatever, star.example.com, you want this proxy command to run, and then it just you get the standard output from SSH as your input to that program, and then you get to do whatever you want with it. And then ultimately you write back to standard output, which is what gets displayed in the terminal. And this local proxy is, like I think I said earlier, that is also a WebSocket client. Okay, so yeah, here's what the SSH config would look like. You can see we cleverly called it Nashville because NASSH. But other than that, we get the host, the SSH host and port, and then we specify this relay host here as well. So what the heck is a relay host? So the relay host is, again, it's like a service. It's a DNS name that resolves to the access proxy IP, but there is one of these per service. And the reason we did it this way, which is actually kind of a shitty reason, but we needed to make a policy decision when the /cookie handler was hit. But for some reason, when Google designed this, they don't actually include what server you're trying to connect to at that point. So we needed a way to say, have per server policies. And the way we solved for this was by mapping the host, the relay host name to the server in the back end. So I mentioned this local HTTP server that we stand up to get the cookie. So yeah, that's, of course, with the Chrome Secure Shell client, it's a browser-based application. It's able to inherit that credential just by design. But for the local on-demand proxy, we needed a way to get the cookie that we get in after hitting the /cookie handler back to the local proxy so that we can stand up the WebSocket connection. So the server just redirects to localhost on an ephemeral port, and then eventually that's what we actually use when connecting to the access proxy. So now I'm going to go over the actual steps of how this works with OpenSSH. I won't cover how it works with Chrome Secure Shell because it's basically the same thing. The only difference is that rather than redirecting to localhost, it redirects to Chrome-extension. So the first thing the user would do is type SSH at user@example.com. Proxy command launches our local proxy and then passes it the standard output from SSH as its input. The local proxy then hits this /cookie handler and provides a callback local port, like the ephemeral port, and then initiates an SSO flow. And then the server finally will redirect to localhost on that local ephemeral port, and then pass in the cookie as well as some other information. So then the client is responsible for hitting this /proxy handler, which again is what is responsible for creating the TCP or establishing the TCP connection to the back end. We generate this session ID, which is just a UUID, and then tie that to a session object, which we just keep in memory, and then establish the TCP connection to the back end. We keep track of those connections in the session object, and then we have a callback that fires when we receive data from the back end. And then finally, we return that session ID, the UUID, in the response body, so that the client knows to use that when establishing the WebSocket connection. So this is an example of what that session object might look like. Sorry, not sorry if you don't know or hate Python. But basically, we just need a way to keep track of the connection to the TCP connection to the back end, as well as the front end connection to the WebSocket or WebSocket client. And also, in here we keep track of the retransmission buffer, as well as the read and write count, which are that ACK that I talked about earlier. So you can imagine we'll just say we have a sessions object. We'll just keep that in memory. It's a global variable maybe. And when we hit the /proxy handler, or when a client hits /proxy, we'll create one of these sessions, assign it to that UUID, and then just add that to the sessions object that we're keeping in memory. It's simplified, but that would basically do it. So then /connect, which is the final handler. Here the client will connect to /connect and provide that session ID, which is the UUID, as well as the ACK and pause, which are read count and write count respectively. The server responds with HTTP 101 switching protocols, and then at this point we just have callbacks that fire when we get new connections or when we receive WebSocket messages. And then, like I mentioned previously, the local proxy just takes its standard in from SSH and then passes that to the access proxy. Whereas the data that we're receiving, like the WebSocket frames that are coming in, we unpack those and then write to standard output, which gets displayed in the terminal. So this is what the connection made callback might look like. So this is when a new WebSocket connection is established. We would look up that session ID, which is the UUID provided in the query string, and then just point to this WebSocket connection in the session object, and then update the read and write count, which are that ACK, which is provided in the query string on new connections. And then we trim this retransmission buffer using the ACK that was provided. So for new connections, it would be 0, and the retransmission buffer would be 0. So we just send an empty WebSocket message on new connections. But in the case of an actual reconnection, there would be bytes in our buffer that we would send to the client. So not going to go over all this, but just in case you're interested in implementing something like this yourself, this is obviously it's simplified, but this is what the connection made callback might do. This is when you get a new WebSocket connection. And then what do you do when you receive WebSocket messages? So we take the message and then we increment that write count, which is the ACK. Or actually that's the pause, but anyway, increment the write count, ignore the 4-byte ACK in the message. We don't calculate we don't include that when we calculate the write count. And then we just pass the message on to the backend service. So it's the bytes in, bytes out, basically. We just, except for the 4-byte ACK, send everything else to the backend. And then trim the retransmission buffer using the ACK that we provide, or that was provided by the client. And then this is what the message received function definition might look like. If you're interested later, look at the slides. So then data received, this is when we receive new data from the SSH server. So for this, we update the read count, and then we concatenate the write count that we've maintained with our data, and then we just send a WebSocket message to the client with the data that we received. And again, that's what that might look like for the data received function definition. And so miscellaneous things. There were a few gotchas. I mentioned that Chrome Secure Shell doesn't honor the close control frame, the WebSocket close control frame. So if you really want to close the connection, the way you can do so is by sending a negative ACK with an empty payload, or probably any payload. That'll trip it up and it'll terminate the connection. And then this other one here, if the retransmission buffer that we keep isn't sent when a new WebSocket connection is made, it's possible for a race condition to occur because we've separated the /proxy step from the /connect. It's possible that you would get the first part of the SSH handshake, which is the version from the server. And then if we just if we don't do anything with that data, the client will send its version, and then the server will respond with the key exchange because it's like, I already gave you the version, but those bytes were just discarded. So that's why it exists, I guess, is because the slash proxy is when we create the TCP connection, and slash connect is separated from that. So, and in practice, that only happened when I was testing on local VMs because of the round trip time from the Access proxy to the SSH server. So I talked about SSH, tunneling SSH traffic through this Access proxy, but what about other protocols? The good news is it of course works because we're just tunneling bytes. Like, there's not anything special there. So of course, though, not everything is as cool as OpenSSH and has like this handy proxy command facility. So instead, you can just use a socket, like a local socket, and then just have the client connect to this local host, and then you of course just tunnel those bytes through the Access proxy. So quite a few references here. I think I linked to all of the BeyondCorp papers with the exception of maybe the most recent one because I may have made these slides before it came out, as well as some other resources that are available online. I made the slides for this talk available on GitHub. You can use this bit.ly link. It's bit.ly/lc-beyondcorp-ssh-proxy. I think LASCON is also making these available for all of you on the Sked site. Yeah, I'll repeat the question. So he was asking about latency with SSH being an inherently interactive protocol. Yes, I do R&D. I don't do all of the we have teams of people that do load testing and things for products, but I basically just hack on things and see if I can get them to work. It is interesting to when you have this stand up, and you're typing stuff at the command line, just watching every keystroke you type as for every keystroke you type, watching a log message occur. I haven't really noticed anything too crazy. What we did actually test using doing large file transfers over SCP or whatever through the Access proxy, and didn't really notice any significant overhead. So because it's really not doing a whole lot. It sounds kind of complicated, but it's mostly just taking the bytes that it receives and passing that along to the back end. Once it's a WebSocket connection, and not specifically talking about any of the HTTP handlers, but just the WebSocket bits.
This depends on the SSH client having a direct connection not only to the proxy for the WebSocket, but also to the authentication portal. So I'm just thinking of my use case where I typically have Screen, Tmux, Biobu, whatever running someplace, and I SSH to it, and then I do a bunch of SSHing from there so that my sessions are all just kind of sitting there when I get back to them. Mm-hmm. This is modeled on you're SSHing directly from wherever you are off-site to one and only one service within the network, right?
Yeah. So so you're talking about sort of a bastion host.
Yeah, exactly.
Yeah. You could put the this Access proxy in front of the bastion host, but I don't know what benefits that would provide you really, because the whole idea was is to have per server or per service policies for each server that you're connected. Yeah, go ahead.
Yeah, so I guess now that I think about it, one handy thing for this is if you had a bastion host. If you were thinking about using this as a way to remove VPN requirements when you're off-site or something like that, you could just have this. The one service this provides is SSHing into that bastion host, and then you could do whatever. You could do port forwarding or whatever you wanted, but then at least you'd know to get into the bastion host, they're 2FAing, they're doing whatever. So.
Yeah, exactly.
And I mean, this, I guess it would have been cool to actually, I've never used that proxy command thing. It just pops up the web browser? I mean, what?
No. So proxy command, so we've opened the web browser, so we have that Golang client.
Yeah, okay, so
that is just uses, like, for instance, like the open command on Mac OS to launch the
Oh,
browser.
okay. So the open SSH says, goes to some proxy that's local. That's where the magic happens as far as launching something.
Yeah, so proxy command just takes, so basically when you type, so like I showed the SSH config for like example.com. So when you type SSH user at example.com, OpenSSH will read that from the configuration, launch the proxy command, like which you specify, like we pointed to the binary that we wrote, and then then we're responsible for it at that point on. So we wrap the bytes in WebSockets, pass them to the Access proxy, and then ultimately display it.
How ultimately is that substantially less complex or better than having a VPN client, a just general, because you're kind of like having a piece of code that you have to manage on that remote system, which is a big part of why people don't like interacting with VPN clients.
Right, so that's a great question. So I think that one of the benefits is, like, it is pretty lightweight and it's not running continuously. So it's on demand. It only is running, this local proxy is only running when the user actually initiates the connection, then it just shuts down. So it's pretty lightweight. Of course, like, launching the browser, like that's one usability concern that you need to take into account, is like, is this going to throw people off if I type SSH and the browser launches? And then, like, what do you do with the cookie once you've gotten it? Like, you don't want it to launch the browser for every time you type SSH. That would be really annoying. So there's other things to consider, but yeah, that's an interesting point. Yeah.
I can imagine the code server is open source.
It's not.
No.
So the server is a Python thing. The client is Go. I'll give you my card. I'm happy to, like, chat about how it's. I mean, it's like it's not super complicated, honestly. So I'm happy to talk about, like, how it works. Okay. Any more questions? All right. Cool. Yeah, and if you think of anything later, feel free to stop me in the halls or whatever. Happy to chat more about it.